I've been muted. I've been muted the whole time. I hope y'all were yelling at me. That's so embarrassing. I was muted while I was getting ready for this. I've been talking for like 10 minutes straight. Okay, so what you missed me saying, unless you can lip read, is that what I'm talking about today is the custom LLM serving engine that I've been working on. What I just got finished saying is that I was going to show you the project that it's based on while I'm compiling it. As I said, while it was compiling, it is all Rust. The only parts of it that are not Rust are written in C++. Also, there's a Python wrapper, but that's generally for sort of like REPL level. I want to step through a model's forward pass in order to help me and help my agents debug issues that I have implementing models. It's really tedious to recompile that whole thing, so that's why we have that. If you wanted to, you could also implement just about anything you wanted on top of it in Python, but we don't do that explicitly because if you've kept up with what's going on in VLLM right now, they've introduced an experimental all Rust quote-unquote front end, and by front end they mean the actual engine that runs the model, not the model forward path hot loop, or hot path rather. So that, as far as I'm aware, in VLLM is C++. Somebody correct me if I'm wrong. What I got finished saying before that, maybe thankfully I was on mute because I gave a really bad description of tensor parallelism, is what this engine does and why I'm building it. So let me pull up the video and actually explain what's going on here. Okay, so what you're seeing here is me starting the engine. There are two parts to this engine. One is a coordinator or controller. If you are, if you're from Kubernetes experience or background, you'll be familiar with this. So what I did first was start the coordinator. Actually, no, excuse me. I started the worker first. You can see it said subscribed to, actually that happens on both. But anyway, this is the worker. And then what you'll see here is the coordinator. The reason for that is it basically talks peer-to-peer and everything, not everything, but part of that peer-to-peer communication is event-based. So right now, I'm basically in the process of shoring up sort of like reliability of the kind of just the state machine there. Basically what I'm saying is if I start the worker before the coordinator doesn't see it. Anyway, they start communicating. That's what you're seeing here. They will recognize each other's address. And so what we're seeing here is the worker started to load layers 0 to 87, if you can't read that, onto CUDA device 0, which has 12 gigabytes of detected RAM. VRAM. So Nemotron 3 Super is a 120 billion parameter model. That means that at full bit width, 16-bit, it is 120 billion. It's 240 gigabytes just for the weights, and that doesn't include each layer's output. So when you pass the input through a layer, you need to reserve enough memory for each layer to store its output somewhere. So I actually can't read it here. I can actually just go ahead and show you what this looks like to start up. But essentially what I'm looking for here, okay, still building. We have errors. Interesting. All right. Well, I'm not dealing with that right now. So oh, I detached. That's not what I meant. Right. So paste. Right. It's not going to work over SSH. All right. So while that's cooking, we're going to go back. We're going to go back to we're going to go back to the video, right? Okay, so what you are seeing here is okay, so this is loading a reaped version of this model, and if you don't know what a reaped model is, go to Sero's profile. So this is the individual that popularized reap as a technique for local inference. It's not his invention, but what he did was release a large number of models reaped down to various sizes. So what that does is it takes a particular kind of language model called a mixture of experts, or MOE model. So for example, the Nemotron model that we're using normally has 512 experts. And what that means is that each layer, asterisk, because it's not all layers, but after about layer 5 onwards of those 87 layers, each layer is actually broken down into 512 tiny slices, and Nemotron 3 Super is a top 22 model, and so when I say top 22, that means that at each layer, it's going to basically run the token input, the embedded token input, through a tensor. It's going to do matrix multiplication, and that's going to tell it sort of how much each expert lit up. And it's going to pick the top 22 experts that lit up, and then it's going to pass that input to each of those 22 experts. If you've been able to follow along so far, you might be thinking, you only need 22 of those experts in memory, not all 512 at any given time. And that's exactly the insight that REAP leads us to. So essentially what the technique is passing calibration prompts through the model that gives you a rough estimate of how popular each or how often each expert gets invoked. And I'm simplifying somewhat. I think there's another sort of statistical axis that it uses to decide like which experts to keep and which experts to reap. And then it drops for example, I'm using a reap 50. So 50% of the experts have been removed. So it's no longer a 120 billion parameter model. It's now much closer to 60 billion parameters, plus that kind of start of the model that isn't broken into experts. We call that dense. Those dense layers are obviously kept in their entirety. So that gets us down from 240 gigabytes of memory to probably closer to about 120 gigabytes of memory required by just chopping the bottom 50% of the experts right off the model. So that was the first, I think that was the first thing that Sero popularized. The second part is I explained how only 22 of those experts are selected. So once we've reaped 50% of them or 30%, whatever, we can actually offload pretty much the rest of them and only keep 22 experts in VRAM at any given time per layer. 22 experts per layer. So that obviously has a massive impact on how much memory is actually required to run the model. And that's how you're actually seeing this. Let's see. That's how you're actually seeing this in a moment. Okay, so let me back up a minute. So as this is loading, you see kind of up here that VRAM is loading up. It's at about 5 gigabytes right now. That 5 gigabytes is the dense backbone. Backbone is what they call kind of the part of the model that's sort of the core of the model. So you can kind of trim weights off of the MOE layers, but the backbone can't really be meaningfully just kind of cut in that way. There are ways to reduce the size of it, and I'll talk about that in a second. But yeah, so that's what you're seeing up here. And then over here, you're seeing the host RAM. And so what I'm doing is loading 24 experts into video memory, and then I'm loading the other 232 experts into host memory. And then I'm going to swap experts in and out of video memory and host memory as they're needed. It's just a simple LRU, or least recently used cache, which is actually not the optimal kind of cache to use here, but it's good enough to actually get real-time inference out of this. So the video memory doesn't load up quite yet. It's still busy loading up. Host RAM. And the question I ask it is, explain the difference between quantum computing and other stochastic computing paradigms. What I'm doing here is trying to test uncommon knowledge, trying to test, it's not knowledge, but kind of trying to test patterns that are going to be really obvious if we've kind of like warped how they're encoded. So if we've preserved the model, you should be able to see intelligence, and if REAP has destroyed the model, or if quantization has destroyed the model's actual performance and the sort of language patterns that it contains, we should be able to see some obvious sign of that. This is not a scientific test, but I encourage you to do this with like Qwen 2.5 or Qwen 3.5. You will not get the same quality of answer. Okay, so notice that this is completely loaded up. So we're at about 11 gigabytes now, and we're at about 55 gigabytes of host memory. And inference starts out as kind of a blip on my GPU. The reason for that is we don't know which experts we need yet. So chances are probably about 50% of the experts we have loaded up or more are going to be the wrong ones for the first token we pass through. And that's just going to cause everything to grind to a halt right off the bat. And then you see a couple more blips here, and then it starts to kind of scale and almost stay at 100%. The only reason why you don't see the GPU peg out at 100% is because once it kind of reaches its peak, it's no longer swapping out 22 out of the 24 experts or 18 out of the 22 experts it needs every time another token is passed through. Statistically, the experts you needed for the previous token are almost all of the experts you need for the next token. So what that means is that you're going to go several tokens potentially without having to swap at all, and that scales with the number of slots. So if I were to use 22 experts here, this wouldn't go past this kind of small blip here, because we have 22 slots, and each token requires us to potentially have to load any one of those 22. We're going to have to swap one or all of them out of VRAM and swap it with something in host memory at every token, at every layer, actually. So it's not performant. What this shows is that once you add another 2 expert slots, that jumps quite considerably. What you don't see here is how much the CPU memory slots make a difference. So I use 232 here, and I peak out at about 4.5 tokens per second. If I were to use like 72 expert slots, I would get half that performance. So if you've been in a computer science classroom, you will understand how caching 90% of what you need is actually much better than a 90% hit rate most of the time. Ideally, most of that data is very commonly reused. If you only ever need 10% of that data, caching 90% of it is far more than you need. That is the case with LLMs. So we see it spin up here. And if you pause and you're able to zoom in on this, you'll actually get a very coherent explanation. It's using the formal symbols from quantum computing. So the set of mathematical symbols that quantum scientists typically use to express their Hamiltonians is exactly what you're going to see it use. The other thing that was anecdotal, but which I was surprised by, is I don't know if you can see it here, but if you give Nemotron 3 Super a logic problem, it will use formal logic symbols in its thinking block. That is not something I've seen any Quen or really any model that I've been able to run on my local machines do before. So is it a meaningful step up from Quen 9 bil? Yes. Enough to justify going from about 75 tokens per second to 4.5 tokens per second, not unless you're running prompts overnight. If you are running prompts overnight, this is going to change your world. Okay, so the last thing that I wanted to show from this is there's a blip right here, and that blip corresponds with this table being output. At this point, I was kind of just slack-jawed, because basically what's happening here is the latency of swapping experts is visible on the GPU utilization graph. So anywhere you see this rate drop, like dramatically like this, like I don't know if you can see this on my screen, it hits 0 for a moment, then picks up, see a small blip. I pause here so that you can see that this is not just an explanation. Nemotron compared quantum, stochastic, neuromorphic, reservoir, and analog computing, and it gives, as far as I can tell, I'm only familiar with quantum and to some degree stochastic computing, but this was an impressive explanation. Now here is where things start to get kind of weird on the graph. That is a wow moment to me. Now it's possible that it's swapping experts so heavily here because it's outputting this graph that is, let's see if I can, no, I don't show that at a higher resolution. Yeah, but it's slowing down here to output this graph because it's swapping experts. So you can visually see that different experts matter for different kinds of tasks, like prose versus a structured table. And then I pause here just to show that this is a pretty reasonable kind of demonstration. If you couldn't actually read the rest of this, this makes it pretty clear that Nemotron isn't just making things up. All of these concepts actually exist in its corpus. And you probably won't see the same things emerge from, for example, like Nemotron Nano 30B. Okay, so that's the demo video. The last thing that I didn't mention is that we're using quantization here. So how do we actually get this down from still being, 60 billion parameters and therefore almost 120 gigabytes to fit on a single 12 gigabyte graphics card? That is quantization. I'm going to go into a lot more depth on what quantization is and how it works in more videos, in more written content. It is a significant amount of the software and technology that I work on, and it's also key to actually getting this to fit on my graphics card. So not only is the model quantized from 16-bit to 4-bit, so actually about 4.65 bits per weight. Bits per weight is how we actually measure the I guess the information capacity or information theoretic capacity of a model. So if you have a model that's able to fit a weight in 1 bit, you have something that's 65,000 times more compressed than like 16-bit. Right, so with 16-bit, you have that combinatorial 2 to the n, n squared. So used to doing quantum computing that I now get those backwards. But yeah, so you have that sort of combinatorial growth, whereas 1 bit is actually much more compressed than just 16 times compression. So 4-bit compression is extremely good. That is kind of the other component of how I'm running this. It's just standard llama.cpp quantization, but for the activations, the activations are Hadamard compressed, and we get 7.7 times compression on the activations, which matters a lot when you're running a model this big. The activations are very large. And then we're also using TurboQuant for the KV cache compression, which gives us about 5.1 times compression on the KV cache, makes it 80 megabytes per, I think, like 8K cache versus about 320 megabytes for 8K of cache with 16-bit KV cache. So that, if you're not familiar with any of this, you may have heard about TurboQuant in passing. TurboQuant the tile-wise Hadamard quantization that I use for activation compression. Those have the same underlying principle. Yeah. And I'm going to be talking a lot more about it soon. Okay, let's take a look at how Codex did. Nothing, because I'm an idiot and I didn't have bypass permissions on. So we're gonna recompile this right now. All right, and while we're doing that, we're gonna check in on our Gemma implementation. So Gemma 4 is Google's latest model. I'm about 2 months late on the implementation. Part of the reason for that is Gemma combines numerous things that didn't previously exist in like published LLMs, LLM architectures. So one of them is shared KV cache. So certain layers share their cache with, I believe, a specific layer. I believe, don't quote me on this, Claude said layer 13 is the actual layer that owns the KV cache for shared layers. Okay, I was incorrect. So sliding shared layers use layer n-2's cache, and then there's a global shared that uses layer n-1. I'm not sure I understand what Claude means by the global shared KV using n-1. Right, okay. So essentially these are different types of transformer blocks. So those are the layers, and each in a lot of models, these blocks are uniform. So Qwen dense models around the era of Qwen 3, each layer is going to be identical, essentially, in structure. With Qwen 3.5, we started to see layers, we started to see things like some layers having an asymmetric number of attention heads. And basically what that means is when you're computing the KV cache, that is, for each token in your sequence, how relevant is token n to every other token? And so every time you pass a token through, you need to compute that score. And so typically there's a fixed number of attention heads. And so each one of these attention heads is going to compute some tensor. And basically starting with like Qwen 3.5, we started to see some layers later in the model have a larger number of attention heads. So the model starts out narrow and then widens out. And this causes what we call the hidden dimensions. So the message is flowing between each layer. What is the size of that? That actually also increases. This means that if you built your inference engine on the assumption that every layer was going to have the same number of attention heads and the same output size, you now have to redesign your inference engine to not make that assumption. Gemma 4 came out a couple months later, and it was even stranger. So I won't go into all of the details, but yeah, so we have some of them described here. So there's basically a setting in the model file that says k equals v. So for global layers, when k equals v is set, the v projection is dropped and k is reused as v. I'm not going to explain exactly the semantics of the k and v vectors on stream because I'm going to get clowned on by LLM researchers. But it's roughly what it sounds like. It's a lookup, k is the key, v is the value, and this is basically a projection that's telling you how relevant each input is to every other input. Attention is essentially the thing that makes LLMs work and not just output kind of like a naive probabilistic word, I guess, like Markov chains do. If you want to know more about that, Google all you need is attention, and that's going to basically give you the primer for it, or someone who's done a simpler explanation of it will do a better job than I will of giving you the overview of what attention is and how it works. So Gemma has some layers that share their KV cache with other layers. It's very strange. I didn't implement it. It's also multimodal. So I believe it accepts images, audio, text, and can output images, audio, or text. That is really troublesome to implement if you assume that every model is a pipeline with sort of one edge at the start and end of the model. So over the past month to month and a half, I have been redesigning my inference engine not to assume that a model simply has one input and one output node or edge. That's very challenging, but I'm implementing Gemma 4 now because I've finally actually nailed down the architecture that I want for that. Okay, I'm gonna take a break there and ban some of these spam bots in my channel. Looks like Twitch might have gotten it. Okay, I'm authorizing multi-chat. So, okay, so that gives us YouTube and Twitch, but I'm so sorry, Twitter people, if you're talking to me, I need to check the replies. Yeah. All right. Well, shout out to Rick. Rick's the only one in chat right now. Shout out that. Anyway. Okay. So, yeah. Gemma is what we're in the process of implementing now. Custom attention, Gemma 4 decoder block. Let's see on post normal transformer block for, okay, yeah. All right, cool. That's my job. This is the rest of my job. No, I'm kidding. So all right, so I'll proceed with this. Not implemented ISQ/GGUF serialization targets. So these are types that I've implemented recently. Obviously, you can tell if you look at upstream candle. Candle is Hugging Face's tensor framework. So you can think of it like PyTorch, but entirely in Rust. For obvious reasons, that makes it vastly superior to PyTorch. The one problem with Candle is that it was built assuming that all hardware just works the same, and you know, if you implement like matrix multiplication or kind of any other basic matrix operation in Rust, it's just going to perform fine wherever it is. That's not actually an okay assumption to make. So the difference between my candle and Hugging Face's candle is that there is 0 CPU side rust in the hot path. And the reason for that is my candle supports CUDA graphs. And every time we hit the CPU, every time we have to do device synchronization and move data between these two devices, that stops the kernel in its tracks, and then we have to dispatch another GPU kernel. That's like literally upload code and say run it. That's very slow. So the key to beating Llama's performance is never doing that. Not even when you actually get your results out of the end of the pipeline, and you actually start sampling tokens back from something we call logit probabilities. So logit probabilities are basically every model has a vocabulary. That vocabulary means what tokens does it understand and what tokens can it output. At the end of the pipeline, you get a matrix back, and it is basically a normalized vector that says, what's my probability of each of the tokens in my vocabulary? So don't think of it as like words, but think of it as like almost like syllables. But you can also include punctuation, numbers, things that are kind of indivisible units of text that you might have to chunk and give to an LLM as sort of one unit of information. So the word that's 1 unit of information. The number 150, that might be 3 units of information. Unless for some reason 150 exists in the vocabulary for a model. Usually it's a waste of vocabulary to do that. Okay, so even when we are deciding what token is going to be output next, we never force the GPU to synchronize. The GPU just starts outputting to a buffer all of the tokens it selected, and you can read them back on the CPU side asynchronously. And that keeps everything moving very, very fast. I believe Llama, last time I checked, on my 4070 Ti got 70 tokens per second. I get 75 tokens per second on Qwen 3.6. And I think we might be able to show you that. All right. So it's Mies run, and then we want Nemotron 3 super. Yeah, and so if you've missed it, this is the model that's normally 240 gigabytes just for the weights. And I'm going to run it on a 12 gigabyte graphics card. It's going to take the entire 12 gigabyte graphics card, and it's also going to take 50, well, it's going to load my system memory up to, it's going to load my system memory up to about 58 gigabytes. So whenever I'm working, I have these two views up. I'm in Codex, and I'm in this thing. Another reason we use Rust is this is what Rust looks like, okay, when it's doing work. It's pegging, what, 18? Oh, you can't see all my cores on here, huh? I have 24 cores on this, and they're all hitting 100%. You're not going to get that with Python, and that was the impetus for building this entire thing. When I say that, what I mean is, again, if you missed the start of this, I'm going to take a MacBook, and I'm going to take this 4070, and the MacBook is going to handle like the first 4 to 10 layers of an LLM, and then the 4070 is going to handle the last 10 layers of the LLM. And it's going to pass the tokens back to me. And that software works. I actually had my MacBook and my NVIDIA desktop cooperating in this way back in January. Now that TurboQuant is kind of mainstream and kind of the bar, it's also GPU accelerated. So basically, we can start at like layer 0 on my MacBook and do 1, 2, 3, 4. And then when we send it to layer 5, it's going to go over Wi-Fi to my desktop. Sorry, it's going to be processed by my MacBook's graphics card. It's going to be compressed by my MacBook graphics card. Then it's going to be shipped to the CPU, to the network device, over to my desktop. Then it's going to get uploaded to the GPU in compressed form, and it's going to get decompressed there, and that is, and then it, continues on its way, uncompressed. And we get about 7.7 times compression. So if you were going to saturate a 1 gigabit connection, trying to do this loop before, now you only need a 128 megabit connection. That's a big deal. Okay, so build's passing, it's not passing. diffusion loader type. Found option. Right. So some of our arguments are misaligned due to API changes. So my theory for this one is that interesting. My theory here is that I've been basically implementing embeddings, text to speech, speech to text, diffusion models, video diffusion models. What else did we run into here? Speech loader type, yeah. It's weird that that's an option though. I hope I don't look at this code and find that it's like absolutely cursed. Oh yeah, no, this looks correct though. We're just missing the like transcription variant in the enum because transcription didn't exist before. Right, so the other thing that I was talking about is the engine that this is based on. It is written in Rust by, let's see, where are we here? It's written in Rust. It was originally authored by Eric Buehler of Hugging Face. Shout out to Eric Buehler and Laurent Mazer. Apologies if I'm pronouncing that wrong. Laurent Mazer is the co-author of Hugging Face. Yeah, okay. So the Candle repository is on Hugging Face's GitHub. But yeah, I mean, a massive thank you to Ivar and everyone who works on this. And then let me see if I can find Laurent in here. Yeah, so Laurent Mazer is I mean, he's the primary author of this repository. So most of the code in here was originally written by him and then open sourced under dual Apache and MIT license. Now I'm willing to, of course, share this because I strongly believe in open source, and frankly, if I didn't have kind of market forces and my sorry, I'm getting messages on dating apps. I guess it's a Friday night. So the reason I'm willing to share this information, despite the fact that, you know, this information combined with this repo is my moat, because there's no way you'd be able to catch up in less than 2-3 months. Even though I think actually, where is it? Candle. So is my candle private? No, my candle is private. Okay. Yeah, it is private. I would like to change that at some point, but I need to have the kind of traction that allows me to, you know, do the kind of GGML move that, and when I say GGML, I mean the company that produces llama.cpp. In order to be able to open source this, so that more of us can have access to more powerful local models and be less dependent on cloud-hosted models that farm our data. I have to be able to pay my rent. So when I can pay my rent, publishing this and my version of this, I will do that. In the meantime, you will have to integrate CUDA graphs, a lot of kernels. It's a lot of kernels. You're going to have to integrate Flash Infer. You're going to have to write Flash Infer for Apple Metal. You'd have to do MOE offloading for Apple Metal. Yeah, a lot of updates. So I had essentially tried a version of my software that was built on top of PyTorch and a lot of Python instead of Rust. And that's when I realized that Rust actually does make the difference. And before this point, and you can ask Kai Siren about this. Coily Siren, if you don't know them, go look them up. SRE of 12 years. I had a good long argument with Kai about at what point do you refactor your code to be all Rust and get rid of the Python. And my argument was that we have UV loop, we have Python just-in-time compilers. It's actually not that. It is not worth the sheer amount of time you're going to spend compiling Rust to completely refactor, unless it's incredibly performance critical. Well, this is where it becomes incredibly performance critical, and it seems VLLM is also learning that lesson right about now. So that's how I'm able to eke out about another 5 to 7 tokens per second over Llama. And this difference gets more dramatic the more time you spend actually looping rather than doing matrix multiplication, the heavy part. So the smaller your model, the more it matters how fast your engine is. And that is why it actually turns out to pay off to write it in 100% Rust. So once again, thank you to Laurent Nazaire and the 261 contributors to Candle, along with Eric Bueller. Okay, so let's give this one more shot. I'll be honest, this was going to be a test stream, and what's on this machine is like very much in flight, so I didn't really expect this to just like work off rip. We'll give it one more shot. Did I? I will admit, this is probably a bad use of AI, but I have gotten so used to working on another machine that requires me to basically have Zed open and remote it into something in order to see the code I'm actually working on. The downside to this is that I haven't seen code in a considerable amount of time. Still more performant than Llama and VLLM. Okay, so let's check back over here real quick. Major milestone landed and pushed. Look at that. We have Gemma 4. Yeah, all you need is attention. This is an example of the kind of output that you get with a bad attention implementation. So we get repetition here as well as tokens that just aren't in most words. Even an unprintable ASCII character and Sanskrit question mark. And then the English here, this may be one token, but is more likely sup and one. And so that's typically what you're going to see for like English tokens or Latin languages, right? A lot of the times you're going to see syllable length tokens. Okay, so I'm actually going to let's add a preset for Mies. What fits in 12 gigabytes for Gemma 4? Dense and offloaded MOE. So I'm very curious to test the larger MOE Gemma 4. If you keep up with local models, you will hear a lot of people talking about how Qwen 3.6, 27 billion, is actually more intelligent than Qwen 3.6, 35B, A3B. That A3B means active 3 billion parameters. So it's a mixture of experts model, and not all of its parameters are active during each forward pass. So only 3 billion of them are actually active. And that's the number of parameters roughly that we're going to want in memory, plus, you know, some headroom if we want to actually get a better hit rate on our expert cache. All right, that was an absurd amount of talking. Let's see if Rick is the only one still chatting. Leave me a reply. Like if you're watching right now, say something on this video on Twitter, because it says there's 21 people watching, and I'm not sure I believe that. Y'all not making no noise. Okay. Hello, and Faizan, if you're here, I just saw your message. I will try to remember to get back to you before the weekend is over. If anyone needs me next week, I'm going to be having jaw surgery on Monday, so I'm going to be out of commission for some time. So if it takes some time to get a response from me, yeah, it's because they're gonna smash my face. Okay, so let's check back in over here. Earlier compile the default binary, but not the CUDA, because the default features are empty. did you change it? Oh, okay, it did change that, right? Yep. Okay. There we go. All right. So this is the coordinator. If you've ever used Parallax, that's like the toy version of this. So you run the like the coordinator or whatever the server, and then you run the worker. So let me sorry, I'm trying to remember my tmux key bindings. Excuse me. Shift 5, okay. Right, so we shift 5. That didn't fucking work. I'm sorry. I'm gonna have to go look at what tmux bindings I set. All right. Okay, so then we start the worker, and that should be almost it, except we don't use the TI backend anymore. Profiling, I think we might need. It does not contain profiling. Ah, okay. Profiling is just on by default in Geodesic. Okay, so see how fast this starts up here? Like, all right, I'm gonna flip over here, and I'm gonna have to actually make this smaller. All right, you see the RAM loading up? So the dense backbone loads up. This is what I was showing earlier. It's going to stay at 5 gigs. And so it says it's allocating slabs here. So basically it's like pinning memory to reserve it so that it doesn't get like moved around. Yeah, so where are we at? We're at 56 out of 60 gigabytes consumed. You always wondered, what do we need all this RAM for? I never actually used the full 60 gigabytes of RAM. This is what it's for. This is what it's for. All right, now I'm going to show you something else that's pretty sick. What else does Geodesic come with? Well, it comes with what? Oh, they got SSO now. That's nice. It's not going to let me do that, huh? All right, so we've got Open Web UI, but we actually also don't need to use that because oops. We also have Light LLM, and Light LLM is probably actually going to be more instructive here. Okay, so one of the reasons it's going to be more instructive. I haven't touched this. I haven't touched Light LLM, okay? Haven't set it up. Have not configured it. It does have my model already set up here, though. Okay. Now, let's go talk to it. Let's go see what happens. All right, so this is the familiar demo view. Let me pull that back up, actually. Yeah, let's explain quantum computing. I'm not going to use the exact same prompt because one of the things I actually want to test here is I had a bug before where you might see people online, if you look up REAP, you might see some people say that it's like a broken technology. I thought what they meant was that sometimes, depending on which prompt I put in, it would either echo the prompt back at me, it would just immediately terminate its response with no output, or give me that really long explanation in comparison of quantum computing and different kinds of stochastic computing. And I couldn't figure out why. And then I realized that I was processing multiple tokens at a time. So if you process like 8 tokens at a time, and each token needs 22 experts, you can end up loading more unique experts than you can actually fit. And that just broke everything. But I believe I have fixed this. All right, so there we go. So there's a little bit of CPU processing happening, and then you can see the GPU starts to spin up, but this is slow. This is like slow. But what's happening now? It's getting faster as the cache warms up. Okay, and remember, we can fit 1 token plus about 9% of the experts for the next token. Like 9, it's enough for 1 token and then another 9% of a token. But the number of experts that are reused at each token is so high that we're actually barely swapping. Okay, and you can see here we're hitting about 4.8 tokens per second on a single RTX 4070. This is Nemotron, 120 billion parameters, trimmed down to 60 billion parameters, then quantized so that each of those parameters is only 4.5 bits. And yeah, Light LLM does not do. Oh man, that's a bummer. That's a bummer. So yeah, I would have to kill it and then do another prompt. But you get the picture. I'm trying to think of something that's like actually complex that I haven't done yet, to kind of put this to the test. Now the other thing about this is it's slow, and I want to see actually if let's see, I can't cancel. Okay. So yeah, unfortunately, because I left that page, there isn't really like a way to cancel. I might need to see if there's like if I can do something like server side, so that if someone like disconnects from the like server sent events, like how they receive token updates, output token updates, if I can just like if I can just like kill the response if the WebSocket dies. Okay, so I'm gonna restart this, and this time we're gonna run Kimi 48B. So this is Kimi linear 48B. It uses linear attention. I actually don't know how that's going to work out. Someone online told me that linear attention can't be quantized. And so if we do quantize it, we may just find that output is unusable. But I'm going to test this to demonstrate one of the key features here. So again, boom, faster than Kubernetes. And we're auto downloading the model. I cleaned up models at some point off this computer, but yeah, so basically what you can see here is, you see how this says sync models? So this is syncing the models to Light LLM. So if I go back to Light LLM, can you guess what that means? Let's refresh this page and maximize it so we can actually see. Oh, Kimi's already in here. How did that happen? I must just be like the most cracked inference engineer on the planet. High key though, this is one of the smarter features I've come up with. Yeah, Light LLM also has integration with search tools, MCP tools. I haven't worked on that yet, but yes. So there are kind of various integrations that I'm working on for tools like Light LLM, so that you just spin up the binary, you start my Docker Compose file, and then you have everything from, from like, a web crawler to web search tools to MCP servers. Yeah, I don't think we actually have this like set up to sync with our MCP servers yet. But for example, I can attach guardrails here. Guardrails. So this is actually like a. So there actually isn't an integration between Geodesic and guardrails, but the container setup I have is using guardrails integrated with Light LLM. So you can just use them right from here. This has grown a lot. The last time I checked, Licera existed, Aporia existed, and then Guardrails AI was the only open source solution. Very interested to see what else is going on here. Yeah. All right, well, that is Let's go see if that's downloaded. Over 3 minutes in, and we've got like 20 gigs to download. You know what? This downloading sucks. We're gonna whoops, 26B, A4B, Q4, KM, please. And E4B, dense 6K? Or QK? Or Q6K? That should be fine, I think. This should fit with what do you call it? The multimodal stuff. The Q6K of the dense one. Yeah, that should give me enough room for like audio and video. Where are we at over here? Oh, dang. We're on the wrong model. On the wrong model. Okay, so I'm gonna have Codex look into what the HF hub crate is using for set downloads, and if it's not absolutely stellar already, we're going to research how to write highly optimized parallel downloaders and solve this headache for the entire Hugging Face community. You know what, let me go ahead and put Hugging Face in my stream tags, because them boys owe me a paycheck. No, I'm kidding. Hugging Face, if you see this, hire me. All right. I'm also going to, where's my video capture device? All right, so you see this? Do you see this? I have a gigabit down, like an actual gigabit down. Not like internet salesman gigabit. Like I will actually hit 1.3 gigabytes down, 1300 gigabit. Okay, so where are we at here? So I'm aware of this being an issue from some other people. I believe some other people have actually... Interesting. Some other people have actually... oh. Interesting. Those aren't good defaults. No, we're not going to send an agent here because we're using Spark. So we're going to use the workers CLI flags because it doesn't really make sense to just add arbitrary envars for this. And yeah, I mean, if a real engineer did this, I would shoot them in the kneecaps. So yeah, and then let's make sure we're pulling in Zet extensions, possibly HF transfer, evaluating the other features of the crate for additional performance gains, and we want the Z extensions, evaluating the other features. Optimizing default config. All right. Okay, so we are on latest. Oh, hello. Oh man. I love new releases. I love new releases almost enough not to be afraid of Team PCP. Yeah. This builds in release mode by default. HFRS. Interesting. So they wrote their own Hugging Face client, like a CLI that's faster than the Python version, I guess. Disable automatic token loading, custom user agent. What are the features? Locking and Rust TLS. Interesting. All right, so, okay, right, yes. All right, so we're downloaded, which means that if I go to here, So what I was going to show you before is, yeah, if you're switching models, it's literally as easy as tell the coordinator that you want to use a new model. It shows up in here. What's good, Kimmy? What do you know about quantum computing and how it compares and contrasts to other forms of probabilistic computing? All right, so this is a 48 billion parameter model. I believe it's A3B. Oh, that's different. That's definitely different. $500. 500 would make sense if it was downloading. All right. Oh. Interesting. Okay. We're gonna try a different model. I don't know if I have anything else that's good offloaded. Clean drop-in upgrade yet. All right, so yeah, the other thing that I would actually show you is coordinated API migration for the immediate download tuning. Yeah. Oh, interesting. Wow. This is really a full 1.0 release. Okay. That's interesting. I need to actually update the model for this, and also so I want the Unsloth ultra dynamic 3.6 client. 3.7 isn't open weight yet, is it? Is Quen 3.7 open weight yet? Currently proprietary and closed weight because Alibaba hates me and wants me to die. All right. Give me a quick second here. I'll probably do like another 10 minutes, maybe. Maybe more stream later, because I can't lie, 24 viewers is not bad. 25 viewers. I don't know if Elon is just lying to me. But I'll tell you, that's better than like Twitch off of like no planning, no like prior consistency. Just like starting this back up. I would stream again. I would stream frequently, actually. All right, so we want the unsloth UD 3.6 quant. So we're gonna pick a model architecture like Carbon. Shout out to Zach. What's Zach's last name? To Zach Mueller from Lambda Labs. I actually don't know if it's Labs. If it's just Lambda. Lambda API. Shout out to Zach. I don't remember exactly why. Right, he told me that Carbon was out, so we're gonna pick something like that, and time our download speed with HFRS. To see if the RC is meaningfully faster. Yeah, so if you're still sticking around, if you're still here, you haven't heard the news, I am CEO and founder of Geodesic Inc. As of last week. I am also starting my personal Patreon and Discord community. So that is most likely not going to be directly connected to this work. But right now, for example, I actually can't show you a ton of what I have cooking at the moment because I don't have games installed here. But if you've ever played Valheim or Vintage Story or Terraria or Core Keeper, any of those, style of co-op crafting survival, I host those on my personal cluster, and you will be able to access them along with other services that I'll be hosting. So that will be things like basically a Dropbox alternative that's open source, that you'll be able to get probably up to like a terabyte of dedicated remote storage on. And so as this community grows, I'm going to avail more of these hosted services, essentially just being cheaper than you could possibly get them if you were to get all of your subscriptions separately. Host them on my mini PCs instead. It's all got redundant backups. It is now high availability. In the sort of coming months, I'm going to be working even more on the reliability story for that, so that users can migrate their data elsewhere if they want to halt their subscription. And then let's say 3 months later they want to use their own their own object storage for their backups, or they want to switch to Dropbox. They'll be able to just kind of hit a button and transfer their things there. But if you want to be part of the Cube Doll community, yeah, pitch in for you know, an important community effort and shit, save some money and invest in something that's you know, gonna be here for you a lot longer than most of the online services you use. Okay, that Netflix subscription, that is going up, baby. Um, you know, uh, yeah. So that's the other thing that I'm working on. I will have a Patreon soon where you can subscribe, join my Discord channels, yeah, join my game servers, get your own dedicated storage, hosting, all that good stuff. Maybe eventually your own dedicated Kubernetes namespace. Yeah, that's what I'm working on. Okay, let's see how this download's doing. Go ahead and say that's. I guess it is downloading. Also, okay, yeah, so that's not the right binary. All right, explaining to explaining to my clanker. Okay, and where else were we? So this is my 4070. How are things going on the? There's no PLE, no KV sharing. Yeah, there we go. The per layer varying KV heads. That's one of the weird things. All 30 layers are MOE. It's also kind of shared dense FFN with a weird intermediate size. Yeah. I don't know. Google must be on some whole other shit because this is an unusual architecture. This is fascinating. Make PLE optional, embedding length per layer input. Dense FFN plus MOE FFN, both with their own pre-post norms, combined then post-normed. Okay, so I'm sorry, Gemma for MOE FFN is fucking what? This is really bizarre architecture. And so when I say that, I mean that, um, first of all, variable attention heads and variable attention heads plus layers that share KV cache is yeah. Um, it's like a bunch of things that you don't see in other architectures all like rolled into one thing. Six different research papers stapled together into one decoder layer. Okay. Standard attention, but with everything weird. Q, K, and V get their own, what is that, root, RMS norm, root. I'm not going to attempt to embarrass myself. V has no learned weight, just normalize. Interesting. Right, root means square. Okay. Yeah, that's what I thought. Okay, so per layer, head dim flips, 256 on sliding layers, 512 on global. Right, and then KV head count, 8 KV heads on sliding, 2 on global. That's what I was referring to earlier. Probably didn't describe it perfectly. On global layers, only the first 25% of the head dim pairs get rotary positional encoding. The rest pass through. Uh-huh. Then a hybrid feed forward block, which is 2 parallel branches summed. That's interesting. Running those in parallel is weird. So, yeah, I'm wondering if the reason that their MOE architecture has a parallel dense feed forward is because Google actually meant for that to be parallelizable. Okay, well, that's going to take some time to cook. All right, let's see. Grabbed an MTP. Yeah, I have not even touched the topic of speculative decoding, but that is also, of course, on the way. So speculative decoding, God, it's already 12:30. I don't know if I'm gonna explain speculative decoding after midnight. I think you gotta pay me like double time for that. Oh, dang. X is finally killing communities. Oh, well done. Yeah, so, okay. Same harness against, so we have an apples to apples. Um, right. So, yeah, people who are kind of as deep into this stuff as I am probably already know that there are multiple kinds of speculative decoding, and essentially what speculative decoding is putting a second draft model or some other kind of model. Some are capable of self-speculative decoding. And using that to kind of predict or guide the next token or the next n tokens. And that can, in some cases, give you as much as a 200% speed boost. It is, along with the things that are happening in quantization, what is going to really start closing the gap between local inference and cloud-based inference. I mean, for example, if you could get the 5 tokens per second that I was seeing on this card to be 10 tokens per second or 15 tokens per second on a model like Nemotron 3 Super, now it makes increasingly less sense to rent a B200 just to check your emails. And that's really what I'm trying to achieve. I think that AI is capable of a lot, but the fewer B200s we need to use to achieve it, the better off we're all going to be. And that's why you see me doing this. Yeah, okay, so I don't know if there's too much I want to show tonight. This shape is TPU shaped. Okay, that is what I thought. Functional decomposition rather than refinement. Yeah. All right, well, it's almost 1 a.m. here, and honestly, I'm not going to be able to keep talking about LLMs in a way that's coherent and useful to anyone. Yeah, follow me on Twitter, follow me on Twitch, follow me on LinkedIn. There's going to be a lot more stuff coming down the pipe.